You know, we look for the shortest path dozens of times a day, and we don't even think about it. Your GPS finding the fastest route to work, your emails zipping across the globe, none of that is magic. It's actually the result of this fascinating battle between different algorithms, and each one has its own secret strengths and its own hidden weaknesses.
So let's just start with what seems like a really basic question. What is the shortest path? Now, before you jump to an answer, I'm going to tell you right now, the obvious answer is almost never the most useful one.
And this really gets to the heart of it. It breaks a huge assumption we all make. When we say shortest, are we talking about the fewest miles or the fastest arrival time? Avoiding all that traffic. Maybe it's the cheapest route, dodging all the tolls. Or heck, maybe it's even the safest route with the lowest risk. The word shortest is totally dependent on what you're actually trying to optimize.
And that right there brings us to the most important point of this whole thing. These algorithms, they're not fortune tellers. They're just very, very carefully tuned tools. And they only give you the right answer if we've correctly described the reality of the problem we're trying to solve.
Okay, so formally, this is what we're talking about. We've got a graph, which is just a network of points, we call them nodes, connected by lines, we call them edges. Every edge has some kind of cost. And our job is to find the path from a start node to an end node that has the absolute minimum total cost. Sounds simple enough, right?
Well, not quite. See, hiding behind that really simple definition are some super critical questions. Are all the costs positive, or could you maybe get a refund for taking a certain path? Does every single step cost the exact same? And do these costs change over time? The answer you give to each of these questions points you to a completely different algorithm.
All right, so let's start at the very beginning. Let's imagine the simplest possible world, a world where every single step we take is exactly equal.
In this world, which we call an unweighted graph, every single road is the same. There are no superhighways, no slow country lanes. The cost is literally just the number of connections you have to cross. So the shortest path? It's just the one with the fewest steps. Simple as that.
And the perfect tool for this job is something called breadth first search, or BFS for short. Think of it like dropping a stone in a pond. The ripples spread out, right? BFS explores the graph just like that, in these radiating circles, one level at a time. So it checks all the paths that are 1 step long, then all the paths that are 2 steps long, and so on. Because of that, the very first time it hits the destination, it's guaranteed to have found the path with the fewest possible edges. But, of course, the real world is almost never that simple. So, now let's introduce a complication that completely shatters our nice, simple BFS approach. What happens when different steps have different costs?
And here is where it all falls apart. Look at this. BFS only cares about the number of steps, so it sees that 2-step path from A to B to C and thinks, aha, that's the winner. But it's a trap. That path has a total cost of 10. Meanwhile, the longer path, the one with 3 steps through D and E, has a total cost of only 6. BFS is completely blind to the actual cost of the journey.
So here's the big takeaway. In a weighted world, fewer steps does not mean a cheaper path. Our simple tool is officially broken. We need something smarter. We need an algorithm that can actually think about the total accumulated cost as it explores.
So, how do we solve this? Well, enter the classic, the one and only Dijkstra's algorithm. It's a tool that was designed specifically for this world of weighted graphs. Dijkstra's is kind of brilliant because it's both careful and what we call greedy. It starts at the source, and it always expands its search from the node that is currently the cheapest to reach. At every step, it looks at its neighbors and basically asks, hey, does this new path I just found offer a cheaper way to get to you? Once it's absolutely positively sure it has found the cheapest path to a node, it locks it in and never looks back. It just keeps repeating this, greedily picking the next best option until the destination itself is locked in.
So why is this greedy strategy safe? Why doesn't it make a mistake? Well, it all hinges on one massive assumption. All of the edge weights are non-negative. If every step you take can only add to your total cost, well then once you find a path to a node, you know for a fact that any other path that eventually gets there is just going to be more expensive. A path's cost can never, ever get better later on.
That non-negative assumption is the source of Dijkstra's power. And as you might have guessed, it's also its greatest weakness, its Achilles heel. So let's introduce the one thing that can bring this whole elegant system crashing down.
Just imagine a path where one of the edges is like a rebate or a discount. It has a negative cost. Dijkstra would lock in what it thinks is the cheapest path early on, completely clueless that some other longer path could later take that rebate edge and actually end up with a much lower total cost. Its entire core assumption has been violated.
And this reveals a fundamental truth that goes way beyond just programming. Greedy algorithms, the ones that make the best-looking choice at each step, they only work when they have a property called monotonicity. And that's really just a fancy way of saying they need a guarantee that the situation won't suddenly get better down the road and make their earlier choices look foolish.
So what do we do when we can't make that guarantee? When negative weights are a real possibility? Well, we need a more patient, a more skeptical algorithm. We need Bellman-Ford. If Dijkstra is this optimistic explorer racing ahead, then Bellman-Ford is more like a meticulous detective. It doesn't trust any of the early results. Instead, it just reevaluates every single edge in the entire graph over and over again. It's this slow, repetitive process that allows the truth about those tricky negative weights to finally bubble to the surface and spread through the network.
And this really lays out the trade-off perfectly. Dijkstra is fast, it's efficient, but it completely fails if you have negative weights. Bellman-Ford is way slower, but it's tough, it's robust, and it can handle them just fine. So the choice comes down to one between optimistic speed and cautious correctness. There's no single better algorithm. There's only the right one for the assumptions you're able to make.
So far, we've really been focused on the type of path we're dealing with, but the complexity also really depends on the type of question we're trying to answer in the first place.
For example, are you trying to find the path from your house to everywhere else in the city? That's a single source problem. Or are you just trying to get from your house to the office? That's single pair. Or what if you're a giant logistics company and you need the shortest path between every single warehouse in your network? Well, that's an all pairs problem, and that requires an entirely different, much more powerful set of tools to solve it efficiently.
Which brings us all the way back to our central theme. These algorithms, they teach us a really fundamental lesson that goes way beyond code. Correctness, it's not some universal, absolute state. A solution is only correct under a very specific set of conditions and assumptions. You change those conditions, and your perfect solution can suddenly become perfectly wrong.
So I'll just leave you with this thought. The next time you're searching for the best, the fastest, the shortest path for anything in your life, just take a moment, pause, and ask yourself, what am I assuming about the world right now? Because understanding your own assumptions, that's always the first and most critical step to finding the truly optimal path.